Okay, in this video, we are going to talk about the analysis of the quantum counting. So recall that we have the following relationship between m and theta. So we have sine of, sine of theta over 2 is equal to square root of m over n. And we are going to use the phase estimation. So phase estimation algorithm with the unitary to be g, the Grover operator. And so using this, the fact that the Grover operator, if I input the uniform superposition state, then you get this relationship between the eigenvectors alpha 1 and alpha 2 of the Grover operator. So the idea of the algorithm was to do a phase estimation using G and then use the relationship. So this phase estimation will give us an estimate of theta and then use uh, this equation 1, to estimate the value of m. Right. So these are the two key equations. And then we had the circuit where we have the top qubits, which were t bits, let's say, t qubits. And the bottom one was n. And we had this Hadamard tensor n. And then we had this Grover operator, 2 to the 0. And finally, g 2 to the t minus 1. Right. And there was some control gates that get applied, something like this. And then we had this measurement over here. And this is where we get the estimate of theta over 2, right? Because it's theta over 2 over here. So now there are two things. One is that um, the number of Grover operations, number of Grover iterations applied are just g to the 2t, right? And so therefore, the number of bits over here determines the number of Grover iterations applied. T also is related to the accuracy of theta over 2. So let's say we want t to be theta over 2. So if I want delta theta over 2 to be, if I want an m bit accuracy, then I need delta theta over 2 to be less than 2 to the minus m for m bit accuracy, right? Now, t will be a little more than the accuracy that we need, and it is related. T and m are related. Suppose I need m bit accuracy, then I need t to be equal to m plus, according to the phase estimation algorithm, log of plus 1 over 2 epsilon, where epsilon is the, so 1 minus epsilon will be probability of success. So if I want, for example, probability of success to be at least 3 over 4, then I should choose epsilon to be 1 over 4. Okay. Now, as I mentioned earlier, we will link the estimate of theta to the estimate of m using equation 1. So let's do that. So linking estimate of theta over 2, I should say, to estimate of m using equation 1. So we have delta m over n is equal to, using equation 1, sine square theta plus delta theta over 2 minus sine square theta over 2. And then I can write this as sine theta plus delta theta over 2 plus sine theta over 2 and multiplied by sine theta plus delta theta over 2 minus sine theta over 2. Simple a plus b, a minus b is equal to a square minus b square. And then we use the following inequality we use from calculus. So this is sine theta plus delta theta over 2 is less than sine theta over 2. And we are assuming theta to be small over here. If I substitute this inequality over here, we get the accuracy of my estimate of m, which is on the left side, is less than 2 sine theta over 2 plus delta theta over 2 into delta theta over 2. Now, delta theta over 2, I'm going to substitute as 2 to the minus m, and sine theta over 2 is equal to square root of m over n. Okay, m is yet to be determined, and we want it will be determined by the accuracy of delta m. So this is, by substituting, I'll get delta m is less than n times 2 into square root of m over n plus 2 to the minus m into 2 to the minus m. So this should be equal to 2 square root of mn into 2 to the minus m plus n into 2 to the minus 2m. Now here is what we want. We want delta m to be of order square root of m. So therefore, we choose m to be equal to n over 2, approximately n over 2 plus 1, something like that. If I do that, then of course, n is 2 to the power n. Then if I choose, so choose, right? If I choose m to be this, then if I want epsilon to be 1 over 4, then I get t to be n over 2 plus 3 because of this relationship over here, right? So if I choose m to be n over 2 plus 1, then I substitute everything. I'll get this to be delta m is equal to 2 times square root of m into 2 to the n over 2, 2 to the minus n over 2, 2 to the minus 1, plus 2 to the n over 2 into 2 to the minus 2 n over 2 plus 1, right? So we'll get this to be square root of m plus um, this is n has to be, this has to be, this is n over 2, correct? But this is n, so this is n. So this will be 1 over 4, which is of order, right? And then, so if I choose m to be n over 2 plus 1, I'll get delta m, which is the estimate of m, which is within square root of n. And how many Grover iterations? So number of Grover iterations are 2 to the t, which is equal to 2 to the n over 2 plus 3, which is of order square root of n. And the probability of success is 1 minus epsilon equal to 3 over 4. So we have improved the number of database calls by a quadratic factor with the same probability of success and the same accuracy.